Now, later on, we're going to learn how to name all kinds of different compounds beyond just alkanes, compounds that have lots of different kinds of functional groups associated with them. I think it's useful to actually learn the names of the important functional groups early on when you're studying organic chemistry. We're going to break down the functional groups into two subcategories, those with carbonyls and those without carbonyls. A carbonyl is nothing more than a carbon-oxygen double bond. It's a really common structural motif in organic chemistry. So let's take a look at those groups first. An aldehyde is simply a carbonyl, that's a carbon-oxygen double bond, that has a hydrogen attached to that carbonyl carbon. So here I've got a few simple examples, and I've drawn these out in a variety of different ways. The first way is a Kekulé structure, the second way as a skeletal structure, and then the third way as an even more fully condensed structure. And I do this because that ending, CHO, is a really common way of abbreviating an aldehyde. And it can be a little misleading, right? It's not very obvious when you look at CHO that the oxygen is actually double bonded to the carbon. If you draw it out, you'll see that it kind of has to be to kind of fill all of the valencies. So if you ever see CHO drawn out, you can almost be certain that's probably an aldehyde, especially at the end of the molecule structure like that. Next, we've got a ketone. A ketone is a carbonyl bonded to two carbons at the carbonyl carbon. And again, I've got a few examples. The first one is a Kekulé structure, and the second one a skeletal structure. Next, we've got carboxylic acids. These are carbonyls that have an OH, a hydroxy group attached to the carbonyl. And again, I've drawn a few examples here with a variety of different ways. I've got a Kekulé structure of a carboxylic acid, and then a skeletal structure, and then a condensed structure. And again, that condensed structure, I really want to call attention to it. You can see that the carboxylic acid functional group, CO2H, it's not immediately obvious that those two oxygens are both attached to the previous carbon and that one of those two oxygens is double bonded, right? So if you ever see that abbreviation, CO2H, remember it's representing that carboxylic acid functionality. Next, we've got acyl halides. These are carbonyls that have a halogen attached to the carbonyl carbon. And again, just a couple of quick examples, a Kekulé structure and a skeletal structure. The next functional group is a little bit of a weird one. Acid anhydrides. These are actually two carbonyls that are attached to a central oxygen atom. So here I've got a couple of examples. Again, a Kekulé structure where you can see the two carbonyls attached to one oxygen and then a skeletal structure as well. Then we have esters. An ester is a carbonyl that is bonded to an alkoxy group. An alkoxy group is just O and then some kind of an alkyl group, often abbreviated as OR, where R just represents any alkyl group. So here I've got a few examples again. I got a Kekulé structure and then a skeletal structure of a couple of esters. Next we have amides. And an amide is a carbonyl that is attached to a nitrogen at the carbonyl carbon. And again, just a couple of drawings here to show you what they look like. And then last, we have a really weird one, nitriles. A nitrile is actually a carbon-nitrogen triple bond, which means it's actually not a carbonyl. But they're almost always talked about when you deal with carbonyls because their chemistry, their reactivity is real similar to that of carbonyls. So here I've got a couple of examples drawn out. I've got one as sort of a Kekulé structure, and then I have one drawn out in a skeletal structure. And again, remember that there is a carbon-nitrogen triple bond, whether it's drawn in or not. That's really common, especially in skeletal structures, to just draw CN without the triple bond, but that triple bond is there. So then we have our non-carbonyl functional groups. Starting off with alkenes. Alkenes are just compounds that have a carbon-carbon double bond. So I've got a really simple example here drawn out as a Kekulé, or actually Lewis structure, and then another one as a skeletal structure. Then we've got alkynes. These are compounds with a carbon-carbon triple bond. Got a couple of examples here as well. And then we've got alkyl halides. These are just alkanes essentially, or compounds that have a bond to a halogen. Next, we've got ethers, which are compounds that have an alkoxy substituent, which is again that OR. It's an oxygen attached to another alkyl group. So here I've got a couple of simple ethers. Another way to look at ethers is essentially it's an oxygen that's bonded to two alkyl groups. Then we've got alcohols. These are compounds that have an OH or hydroxy group attached to them. So again, I've got a simple structure here for one and then a skeletal structure for the other. And then lastly, we have amines. Amines are compounds that have a bond to nitrogen, a nitrogen substituent, and a couple of simple examples here as well. Go ahead and learn all of these functional groups. And again, I think it's easier to learn these by categorizing them into carbonyl groups and non-carbonyl groups. When studying organic chemistry, we often need to know about the degree of substitution of a given atom or functional group. The degree of substitution is simply an indication of how many carbon atoms are attached to a particular atom. The degree of substitution can be applied directly to any carbon in a molecule. You simply count up how many other carbons are attached to that carbon. The terms methyl, primary, secondary, tertiary, and quaternary are applied. So here I've got some examples. This first carbon is considered a methyl carbon because it has 0 other carbons attached to it. In the next molecule, the carbon pointed to here is a primary carbon because it is bonded to one other carbon. In fact, both the carbons in this molecule are technically primary carbons. In the next molecule, pointing at that center carbon, you can see that that carbon is bonded to 2 carbons, so it is a secondary carbon. The other 2 carbons would be primary, right? Because they're only bonded to one other carbon. In the next example, again, that central carbon, it's bonded to 3 other carbons, so we're going to call that tertiary. Again, the other 3 carbons on that molecule are primary. Each one is bonded to only 1 carbon. And in the last example, that center carbon is quaternary. It's bonded to 4 other carbons. We often abbreviate these last 4 substitution patterns with the number and then simply a little degree symbol. So 1 degree, 2 degree, 3 degree, 4 degree, although it's never spoken that way. You always say primary, secondary, tertiary, or quaternary. Now, this idea of degree of substitution can also be applied directly to certain functional groups. For alcohols and alkyl halides, this is how it works. You simply count how many carbons are attached to the functionalized carbon, that is, to the carbon that actually bears the functional group, the OH for an alcohol or the halogen for an alkyl halide. So look at this first alcohol example. You can see that the carbon that actually is bonded to the OH, that carbon is bonded to one other carbon. So that is a primary carbon, so the molecule is referred to as a primary alcohol. Look at the second alcohol example. This is another primary alcohol. Yeah, there's a tertiary carbon in this molecule, right? But when you're describing the functionality, if you're going to say what kind of alcohol is this, what is the degree of substitution, we only care about the actual substitution pattern on the functionalized carbon. And if you look at the carbon that bears the OH, you can see that that is bonded to only 1 carbon, so it is primary. So we call this a primary alcohol. The last alcohol example is a secondary alcohol. You can see that the carbon that is bonded to the OH goes on to be bonded to 2 carbons, therefore it is secondary, so we call it a secondary alcohol. The same thing can be done for alkyl halides. This first alkyl halide is a primary alkyl halide because the carbon that bears the halogen is also bonded to only 1 carbon, and that means primary. The second example for an alkyl halide would be a tertiary alkyl halide because, again, the carbon that is bonded to the halogen is bonded to 3 carbons, and that means tertiary. So it's a tertiary alkyl halide. Now, amines are actually done differently. On an amine, you actually count the number of carbons attached to the nitrogen. And there's actually a really good reason for this. Let's take a look at our examples here. This first example would be a secondary amine because the nitrogen itself is bonded to 2 carbons. And that's one of the reasons why we actually do it this way, because amines can actually have different numbers of carbons bonded to the nitrogen and still be considered an amine. That's not the case for an alcohol or an ether or an alkyl halide. An alcohol will always have 1 carbon bonded to the OH. An alkyl halide will always have 1 carbon bonded to the halogen. And an ether will always have 2 carbons bonded to 1 oxygen. So in an amine, it's a little different. You can have an amine that has 1 or 2 or 3 carbons attached to the nitrogen. So again, looking at that first example, those carbons that bear the functionality are actually methyl carbons. But in this case, we don't care about that. We're not looking at the substitution pattern of those carbons. We're looking at how many carbons are actually bonded to the nitrogen. And since there are 2 carbons, this is a secondary amine. Look at that second example. The nitrogen itself is only bonded to 1 carbon, and that makes this a primary amine. Yes, that carbon that it's bonded to, the carbon that is bonded to the nitrogen is a secondary carbon. But again, with amines, that's not what we look at. We look at how many carbons are bonded to the nitrogen. And in this case, it's only one. So it's a primary amine.